Hi, everyone. In this video, I will be giving a demonstration of the chi-square test of association for a 2x2 contingency table using IBM SPSS. And the chi-square test of association is also referred to as the chi-square test of independence, and different authors prefer different language, but they're referring to the same exact test. The chi-square test of association is generally carried out when you have two or more categorical variables that you are seeking to relate, or basically to test the relationship between. And most commonly in applied research, you're going to see this test applied in the context where you have just two categorical variables that you are relating. In our data set that we're going to be working from, we have two variables, and those variables are both binary. So in this particular case, that's what's producing the 2x2 contingency table that we'll be talking about shortly. So before I actually begin running the analysis, I do want to mention that underneath the video description, you'll find a link to the SPSS data file that I'm working from in this presentation. So feel free to download a copy of the data to follow along. You will also find a link to some additional information that you might find useful and that as a supplement to this discussion. So in terms of the data that we have right here, again, we have two variables. We have a indicator of gender identification and an indicator of whether a person has had a drink over the last 30 days. And this is data that I simulated based on a report from the Oklahoma Department of Health. So in this particular data set, think of each row in the data as representing an individual that might be sampled from the population at large, and where they reported on their gender identification and also whether they have had a drink over the last 30 days. So the gender identification variable is coded 1 and 2 in our data set. The ones indicate a person identifying as male. The twos indicate a person identifying as female. For the drink variable, a 1 indicates a person who has indicated or said yes, they have had a drink over the last 30 days. A 2 indicates a person who has said no, they have not had an alcoholic beverage or drink over the last 30 days. Just so you know too, if we go under variable view and look at the values, you can see I've already assigned labels to these values. So those labels will appear in our output when we run our analysis. It'll make it a little bit easier to make sense out of what's going on. So fundamentally, in carrying out our tests, what we're interested in is determining, is there a relationship between a person's gender identification and whether or not they have had a drink over the last 30 days. So that might be considered our research question. And so we're going to carry out our test to test whether there is an association. For our null hypothesis, it would simply be that there is no relationship between gender identification and drinking behavior. The alternative hypothesis would be that there is a relationship between these two variables. So the other thing too that I want to mention before I actually begin running the analysis is kind of our just talk briefly about the notion of the 2x2 contingency table. So basically the 2 and the 2 that you see right here are basically referring to both of the variables that we are including in our analysis, but more specifically, it's referring to the number of levels for those variables. So we have two variables. We have a drink variable with 2 levels, basically yes or no, and then we also have a gender ID variable with 2 levels, basically identifying as male or female. So in our data analysis, the contingency table that's created, we're going to have 2 rows in the data set reflecting the 2 levels of for the drink variable, basically yes or no. And then we'll have 2 columns, which is the second number right here, referring to gender identification as either male or female. So this is giving you an idea about the dimensions of the contingency table. And if you take the product of these two dimensions, the number of rows and number of columns, that gives you the number of cells in our contingency table. And I'll show you what I'm talking about with that in a second. Obviously, we could generalize this out a little bit further. We could have theoretically a 2x3 contingency table where we would have one variable has 2 rows, the second variable has 3 columns, or we could have a 4x2 where we have 4 rows and 2 columns. So that's the general logic behind this. In the case of a 2x3 contingency table, we would have 6 cells. And in the context of a 4x2, we would have 8 cells. Okay, so let's go ahead and run our analysis. So we'll click on Analyze. We'll go to Descriptive Statistics and then go down to Crosstabs. Okay, so where it says Crosstabs, the next thing that we will do is we're going to move the gender ID variable over to the columns box, and we'll move drink ID over to, or the drink variable over to the rows box. Then where it says Statistics, I'm going to click on that tab. I'm going to click on chi-square and phi and Kramer's V, and we'll click on Continue. And then where it says Cells, we'll click on that tab. And we have by default observed frequency counts. So that's this guy right up here. And then we also have well, it looks like that's about it. So in terms of things that we're going to request, we're going to request expected frequency counts. We're also going to request column percentages and total percentages. And I'm not going to select row percentages just to kind of keep things a little bit cleaner in our contingency table. We'll also select standardized residuals over here. So we'll click on Continue and then on OK. And so now we have our output. So the first piece of output in our data, apart from this general processing summary, is the contingency table. Then the next piece of output contains the chi-square test. And then we also have a measure of measures of effect size. And that's where the symmetric measures table is shown at the bottom. So let's talk then, first begin by talking about the contingency table. Now, I know, the focus of this discussion is the main kind of focus is on the chi-square test, but it's going to be really important that you are able to unpack what's going on in a contingency table, because the test just tells us whether or not there's a relationship, or at least gives us a basis for judging whether there might be a relationship between our two variables. But in addition to making that inference, if you will, we also want to be able to describe what's going on in our data a little bit more precisely, and that's where really the crosstabs table comes into play. So this is like I said, this is our contingency table up here. So as we're looking at it, you'll note that first off, we have our row variable, which is the drink variable. And you'll see that it's broken out into row 1 is referring to individuals saying, yes, I have had a drink. Row 2 refers to individuals saying no. So then we also have the gender ID variable right here. And you can see that column 1 are persons identifying as male, column 2, persons identifying as female. So as we're looking at this, let's kind of look at the row and column marginals first. So you'll see, first off, we have counts. Okay, so you'll see that we have a frequency count right here for yeses and a frequency count for nos. Okay, so this is ignoring gender identification. In fact, it's just cutting across gender identification. So this is the number of individuals saying, yes, I have had a drink. The number of individuals saying, no, I have not had a drink. And down here, you'll see that this is the total sample size, which is 213. So you'll notice too that we have percentages that are given. So you'll see right here, it says percent of total. So the percent of total that you see right here is just computed by taking the 86 and dividing by 213, the total sample size, and multiplying by 100%. So that means that 40.4% of our sample indicated yes, that they have had a drink over the last 30 days. Then you'll see that if we take the second number for no's, the frequencies for no's, 127 divided by the total and multiply by 100%, that gets us 59.6%. So 59.6% of individuals that were sampled indicated no, they have not had a drink over the last 30 days. And again, these are cutting across gender identification. Obviously, too, we could have just said, taking 100% and subtracting the 40.4% right here, and that would get you this percentage here. So either way you want to do it, it's fine. So these values that we're talking about here, these are referred to as row marginals. So we have a marginal count right here. These are the observed frequencies within the rows. And then we have a marginal percentage or marginal proportions, which are given right here. Then if we can also look at this in terms of the columns for our second variable. So you'll see down here, we've got 94 for the number of males. So that's the count for number of males, 94. The count for the number of persons identifying as female is 119. And so as we're looking at this, you can see that we have a percentage of total that's given right here. So in this particular case, if we take the 94 and divide by the total sample size of 213, multiply by 100%, that tells us that 44.1% of our sample identified as male. If we take 119, divide by 213, multiply by 100%, that's going to tell us that 55.9% of our sample identified as female. And these are cutting across the drink categories of yes or no. So we're ignoring whether or not a person has had a drink and just focusing in on overall the percentage of persons identifying as male or female. So these are column marginals. So we have a marginal count, which is given right here, and then a marginal percentage or marginal proportions that are given right here. Okay, so now within our table, we're going to look at the cells. And as I said before, we have 2 rows, 2 columns, so we're going to have 4 cells. So what that means is that we're going to have 4 frequency counts and or observed frequencies. So you can see right here, we have the observed frequency for persons identifying as male who also indicate yes. So we're essentially in row 1, column 1, so 45 individuals who are again male who said yes, or 45 yeses who identify as male. Then in terms of the number of persons identifying as male who said no, well, that will be 49 that's given right here. So that's the count right there. So right here, we just looked at the counts in terms of the number of persons identifying as male saying yes, 45, no is 49. Now, if we take the frequency count for male and for each of those 2 categories there and divide by the total count for male, that gets us a percentage. A cell percentage right here. So you can see right here it says percent within gender ID. So in other words, this 47.9% right here is just calculated by taking 45 dividing by 94 and multiplying by 100%. So, and what that's telling us is that 47.9% of persons who are identifying as male also said yes, they have had a drink over the last 30 days. The percentage that we have right here, the 52.1%, is just calculated by taking the 49, the count for that particular cell, and dividing by 94, and then multiplying by 100%. So that tells us that 52.1% of individuals identifying as male said no, they have not had a drink over the last 30 days. So then if we look at the female column right here, you can see we have frequency counts of 41 for yes and 78 for no. So the percentage, the 34.5% that you see right here, this is just calculated by dividing 41 by the number of persons identifying as female, which is 119, multiply that by 100%. That's the 34.15%. So 34.5% of individuals identifying as female said yes. And then you can obviously see right here that we have 65.5% of females identifying as persons identifying as female said no, that they have not had a drink over the last 30 days. And then obviously, as we're kind of looking at this, just going back to the row, the marginal counts, you can see that the total right here for yes and for no right here is just calculate, we can just sum the counts across the levels of gender identification. So the 86 is just 45 plus 41. For the no's, it's 49 plus 78. So that gets you those numbers. Then the same would be true vertically. If we look at take 45 plus 49 right here, that gets us to 94. 41 plus 78, that gets us the 119 that you see right here. I'll also mention too that from an interpretive standpoint, if you go back and you look at these row marginals right here, the marginal proportions, if you will, you could also use this. I mean, this is describing what's in the data, but you could also think about these as probability estimates for observations that are drawn at random from the population. So you could say, well, assuming that we've drawn our sample at random from the population, our expectation would be that 40.4% of the sample would say yes, 59.6% would say no, or you could say that an average person that is drawn from the at random from the population, that person would have a 40.4% chance of saying yes and a 59.6% chance of saying no. If we look at it in terms of the column proportions right here, then you could talk about it again in terms of probability. You could say a randomly drawn a person, a male who is randomly drawn from the population, or a person drawn at random from the population would have a 44.1% chance of identifying as male, 55.9% chance of identifying as female. And then if we look at the percentages within our cells right here, so we would say right here that if we were drawing a male at random from the population, that individual would have a 47.9% chance of basically indicating yes, that they have had a drink over the last 30 days, and a 52.1% chance of indicating that they have not had a drink over the last 30 days. If we draw a person identifying as female at random from the population, then that individual would have a 34.5% chance of saying yes to that question, a 65.5% chance of saying no. Okay, so that was a lot of discussion about the contingency table. So let's now move on to the main chi-square test. So fortunately, it's not quite as tricky as going through and talking through things in the contingency table. It's actually a lot more straightforward. We're going to focus in on the Pearson chi-square test that you see right here. And what you'll see right here, this is the chi-square test value, and you'll see that you've got the degrees of freedom for your analysis and then also the p-value that's given. Now, the chi-square value that we have right here, the 3.928, that is actually calculated using the observed frequencies and also expected frequencies within our cells. So the 45, the 41, the 49, and the 78 that you see right here, these are the observed frequency counts within each of the cells. Now you'll see too that we have an expected count associated with each of the cells. So we have 38, we have 48, we have 56, and we have 71 right here. Now, the thing is that the chi-square test is essentially, what we're doing is we're essentially testing the degree of difference between the observed frequency counts and the expected frequency counts. And the idea is that if there's greater discrepancy overall between the observed and expected frequency counts, then that's going to signal that there is a relationship between our two variables. And if the discrepancy is very small, and most likely would be attributable to sampling error. In that particular case, that would reflect a lack of association between the two variables. Now, you might be asking yourself, well, how does that actually work, or how does that make sense? But think about it this way: that the expected counts that you see in each of those cells right here, those are expectations that are grounded in the assumption that there's no relationship between the two variables. So, in other words, if the two variables are completely unrelated to each other, these are what we would expect those counts to be in our data. And so, what we have then is an expected count based on the assumption of lack of relationship, and an observed count that would reflect a relationship between the two variables. So, the greater the discrepancy overall between the observed and expected counts, the more likely it is that we have a relationship between our two variables. And then the less of a discrepancy, the less likely of a relationship that we would have between the relationships, between the variables. Or let me state that one more time. Basically, the greater the difference between observed and expected frequencies, it's going to reflect a possible relationship between the variables. And then if there's not a discrepancy, or there's a very little difference between the observed and expected counts, that would signal a lack of relationship between the two variables. So earlier, I had said that basically our null hypothesis was that there's no relationship between our two categorical variables. The alternative hypothesis would be that there is a relationship. We could also specify this in a little bit different way, but still conveying the same idea, and that is that the null hypothesis would be that there's no difference between observed and expected frequencies. The alternative being that there is a difference between the observed and expected frequencies in our data. So the chi-square test that we're carrying out and that we're looking at in this first row in our output right here, basically you'll see that we've got, we have our p-value right here, and really all we need to do is to compare that p-value against our stated alpha, which is our type 1 error threshold. So conventional alpha is set at 0.05. You might set it higher or lower just depending on other considerations, but typically or the conventional threshold is 0.05. And what we're looking for is whether this p-value right here is less than that 0.05 threshold. If it is, then we would reject the null hypothesis and infer that there is a relationship between the two variables. Or in other words, we could say that there are significant differences between the observed and expected frequencies in our contingency table. So either way works fine. So that's really all there is to it. There's not the meaning of this is actually quite simple. So in this particular case, we're going to reject the null hypothesis and infer that there is a relationship between gender identification and drinking behavior, at least as measured using that question. So next we'll scroll down a little bit and we'll take a look at the last table. It says symmetric measures down here. So these are essentially effect size measures, where it says value right here. We have the phi coefficient and Kramer's V. So basically in the context of a 2x2 contingency table, these values will be exactly the same. And in fact, Kramer's V is actually a little bit is a more general version of phi, and it's actually I was kind of reading through David Howell's book earlier, and he was actually suggesting that Kramer's V actually should be, kind of generally, or he preferred Kramer's V to phi as a general rule, just since phi is an instance of Kramer's V with a 2x2 table. So at any rate, we'll just kind of talk then mainly about Kramer's V with the understanding that with a 2x2 table, that those values are going to be exactly the same. So you can see the value is 0.136, and Kramer's V basically runs from 0 to 1. And we can judge the magnitude of the relationship between our two variables in part by referencing Jacob Cohen's 1988 recommendations, or Cohen standards for judging effect size with our test. So I'll just say not Cohen 1988 right here. All right, Cohen. Okay, so his general recommendations for judging the magnitude of the relationship are 0.10 would indicate a small relationship between the two variables. 0.30 would reflect a medium relationship, and 0.50 would reflect a large relationship. So you can see, if you're familiar with Cohen standards or Cohen's recommendations for judging effect size in the context of Pearson's correlation, they're exactly the same. So we're really kind of just using a correlation metric to talk about the relationship between our two variables. So you can see right here that Kramer's V is 0.136, and that would clearly be most consistent with a small relationship. Just keep in mind that the Pearson's chi-square test is testing whether there is a significant relationship or statistically significant relationship between our two variables, but it doesn't say anything about the magnitude of the relationship, only that the variables, we're going to infer that the variables are related if it's statistically significant, and non-related if it's not. So using the effect size measure is useful for describing the strength of the relationship between our variables. In this particular case, the strength of the relationship appears quite small. One final thing that I want to draw your attention to is in our table, we had requested standardized residuals. And so you'll see right here, we have standardized residuals for each cell. And basically, this can be useful for determining which cells are really kind of contributing most to the overall significant effect. And we can even use the values as significance tests. And basically, think about it this way, that essentially the standardized residual, I'll just say SR, for a given cell is equal to the difference between the observed and expected frequencies divided by the square root of the expected frequencies for that cell. And so we can kind of if we assume that these values are distributed as Z, we can use a threshold of 1.96, assuming an alpha of 0.05, as a basis for determining whether there's a significant difference between the observed and expected frequencies for a given cell. It turns out, as we're looking at this contingency table, the standardized residuals, none of those values exceed 1.96 in absolute value. So there does not appear to be any significant difference between an observed and expected frequency within any of the given cells. Okay, so that pretty much wraps up this video presentation. Hopefully you found this useful, and I appreciate you watching.